Okay, so it's lecture 8. And somebody asked this in the chat. So everything up till and including this lecture will be on the midterm, which is next week. And I will send out practice exams for the midterm by tomorrow morning. I mean, you can already find them on last year's course website if you want, but I'll just send an announcement. So, okay. So let's just briefly recall what we did last time. And last time, I want to close up a few loose ends. So last time, we talked about the inverse of a matrix, of a square matrix. And we talked about how to compute the inverse. And the answer to this turned out to be just something we've been doing all along, which was row reduction. And if I had to summarize it in one diagram, it would be this. You take the matrix A, augment it with the identity, and do row reduction until you get the reduced row echelon form, which is the identity if it's invertible. And then what you get in the augmented columns is the inverse. And then we introduced this new, probably somewhat mysterious function at the moment called the determinant. And we actually introduced it in, I mean, we looked at two different ways of computing it. So one was that there was a recursive formula. Which reduced the determinant to determinants of smaller matrices. And then we discovered that actually you could use row reduction to compute the determinant also. And specifically, you know, there were these good properties of the determinant. Namely, it changed in a very predictable way under row reduction. So to compute the determinant of A under row reduction, you just start with the matrix A. Again, it has to be square. And you do row operations, but only swapping and adding. That's enough to turn it into row echelon form. So this is the REF of A. And then because of these good properties, there was a very clear relationship between the determinants of these two matrices. So the determinant of the original matrix was up to a sign, which depends on the number of swaps, equal to the determinant of the row echelon form. Yeah. So in particular, we have two different algorithms for computing the determinant of a matrix. Sorry, can everybody mute themselves if you're not asking a question? Yeah, okay. Okay, good. Okay. And there's one sort of important consequence of what's written in the red box that I didn't explicitly state, at least until the end of the lecture. The important consequence is that, well, A is invertible if and only if its row echelon form is invertible. Because invertibility has to do with the number of pivots, which is true if and only if its determinant is not 0, because we know how the determinant works for upper triangular matrices. But then by this formula, this is true if and only if the determinant of A itself is not 0. So we fulfilled our quest of finding a function that tests whether a matrix is invertible. That's the determinant. Okay. Okay, people are asking if you add multiples. Yeah, add means add multiples of one row to another. And we said in the last lecture, we didn't prove, but it is true. And okay, if you want to see proofs of all these things, they're in the book. They're in section 3.2. But we won't actually cover them in class. You can skip them if you want. Okay, so I want to make two more remarks about the determinant. So one is that there's a good property 3. So last time there was good property 1 and 2, which was behavior under row operations and how the determinant, what the determinant looks like on upper triangular matrices. Good property 3 is the behavior under multiplication. And this property, which is quite amazing, is that if A and B are both n by n square matrices, then the determinant of the product is equal to the product of the determinants. Okay, I find this very surprising because, I mean, from the formula, it just looks like some crazy function, but it turns matrix multiplication into number multiplication. Again, we won't prove this. The proof is in section 3.2. It's optional. But it is a quite amazing property that we'll be using later in the course. And okay, let's check. So so one nice consequence of this multiplication fact is that actually, if A is invertible, then the determinant of A times A inverse is equal to the determinant of A times the determinant of A inverse. But the determinant of A times A inverse is just the determinant of the identity. And what's the determinant of the identity?
One.
So in particular, this implies that the determinant of A inverse is just 1 over the determinant of A. Another really nice property. So that's good property 3 of the determinant. So any questions about good property 3? Okay. And now, finally, I want to end with just mentioning the geometric interpretation of the determinant. So again, we won't be able to prove this, although you can read the book and it roughly says how to prove this. It said, well, if you have a matrix that's n by n, and its columns are v1 through vn, then the determinant of A, its absolute value, that's a non-negative number, is the volume of the parallelepiped with sides given by v1 through vn. Okay, so this is now this is a subset of Rn. So maybe it'll be better if I draw a picture. In 3D, what this is saying is if you have some 3 vectors, let's say that, okay, let's draw some axes. Okay, maybe that's not so good. And then let's say you have some vectors. Let's say you have 3 vectors. So again, this is for square matrices, right? So this is n by n. So let's say I have some 3 vectors. Then the parallelepiped, which I won't rigorously define, again, this is just for visualization, is the sort of generalization of a parallelogram that you would get if you if you viewed these vectors as the sides. Okay, maybe that's not a very good picture, but I hope it conveys the meaning. So in particular, if it's a standard basis vectors, this is just a cube. Okay, maybe I should just flesh it out. It's this set. Okay, and the value of the determinant, the absolute value, is actually just the volume of this. And this explains why the determinant tests whether or not a matrix is invertible. Can somebody say why this gives a proof that a square matrix is invertible if and only if the determinant is not 0, at least intuitively?
Would it be that if the determinant is like 0, then vectors are linearly dependent, meaning that they would like make up an entire plane?
Yeah, that's the right intuition. So if the determinant is 0, then the volume of this thing is 0, which means that the parallelepiped is degenerate. And somehow the vectors lie in a lower dimensional plane, which we'll make that rigorous later, which means that in particular they don't span Rn, or another way to view it is that they're linearly dependent. So this is the geometric meaning of the determinant. Okay. Let me make one last remark about inversion before moving on to the new material, about inversion and multiplication. So the remark is, well, if A and B are invertible, then the product is invertible. And the inverse of the product is the product of the inverses in the opposite order. Okay. So now this might seem kind of odd to you the first time you view it, the first time you see this, but it actually makes a lot of sense because remember, matrix multiplication corresponds to applying a linear transformation, right? Multiplication by A is a linear transformation. And AB inverse is supposed to be the linear, the matrix of the linear transformation that undoes multiplication by B and then multiplication by A. And when you're undoing a sequence of processes, you have to undo them in the reverse order, right? So for example, you know, well, let's think about direction. Suppose I want to go from my house to Ocean Beach, right? Well, okay, so first maybe I'll bike to the BART station, and then maybe I'll take the BART to well, okay, actually I think I have to take a BART to Civic Center, and then maybe take a Muni, and then I get to Ocean Beach. But if I want to go back, I have to do these things in the reverse order, right? Right. So the intuition is when you reverse a sequence of processes, you have to reverse the order. So it makes a lot of sense, actually. Okay, that's the other thing to remember about inverse that's different from inversion of numbers, for example. Any questions about that? Okay, so now let me move on to the subject of today's lecture. So today we're going to do three things as usual. So first we're going to define an important notion, which is the notion of a subspace. Specifically, we're going to talk about subspaces of Rn. Then I'm going to introduce a very important notion for the remainder of the course, which we'll revisit after the midterm, which is the notion of a basis of a subspace. And then finally, I'm going to talk about how to compute two important subspaces, bases of subspaces associated with the matrix. So there are going to be two important subspaces associated with matrix called the column space and the null space. I'll say what those are in a moment. And the last thing will be how to compute bases of the column space and the null space of a matrix. So those are the three things on the agenda for today. Okay. So let's get started with subspaces. So the motivation is you want to formalize some concepts we've been talking about sort of informally already for a while. So we've been saying things like, you know, the set of solutions of AX equals 0 is a plane through the origin, right? Or, you know, at some point we've made statements like, well, the span of one vector, let's say this, is a one-dimensional object, or is one-dimensional, right? But we haven't actually defined what dimension means. And we haven't defined what plane through the origin means. Okay. And so what we're going to do with this notion of subspace is give a rigorous definition that captures this concept. So here's the definition. So again, the heart of the, I mean, in some sense, this is what a plane through the origin means in higher dimensions. So you can view this as a definition of, you know, what a high dimensional plane even is. Okay, so a set of vectors H subset of Rn. Okay, so this means subset of, and subset of, you know, the picture that goes with it is this Venn diagram that there's Rn, and inside here there's H. Okay, a set of vectors H subset of Rn is a linear subspace of Rn. Sometimes we'll just call it a subspace. In this course, subspace will always mean linear subspace. If three things happen. The first is a zero vector is in there. Okay. The second condition is whenever two vectors are in the subspace, if you add them, you stay in the subspace. So if V and W are in the subspace, then V plus W is in the subspace. And the third condition is, I mean, at this point, probably you can guess that if a vector is in the subspace and you have a scalar C, then if you take a scalar multiple, it stays in the subspace. Okay, so what's the picture? Let's just draw what we think. Sorry, let me turn that off. So let's actually, before we draw the picture, let's summarize this more conceptually. So these are three conditions. So 0 in H means contains the origin, right? And conditions 2 and 3 actually articulate that it's a plane. I'll explain that in a moment. Why do these mean it's a plane? But in terms of linear algebra, what this is saying is, well, it's just saying that H is closed under taking linear combinations. So if you take some vectors in H and take linear combinations of them, you stay in H, i.e. H is a non-empty set closed under taking linear combinations. So that's the way I think about it. Now let's look at let's look at why this is supposed to represent a plane through the origin. So let's look at R3. And let's suppose now you have a plane through the origin, right? So that's the origin. And let's say you now have, okay, that's not a very good picture. Let's say you have, a plane through the origin. I mean, I don't know how through the origin that looks. Now, what properties does it have? Well, if you take two vectors in this plane, then certainly you can scale, certainly you can add, you can scale any vector and you'll still be in the plane, right? You can even scale by a negative number. And you can also add two vectors that are in the plane, and you'll get a new vector that's still in the plane. You can't leave the plane by doing these two operations. Okay, so that's why this definition captures a plane through the origin, and this is the essence of being a plane. This is the definition of being a plane through the origin. Okay, so this is why it's a plane through the origin. Right, that if you take all linear combinations, if you look at the set of vectors you get, that looks like a plane. Okay, any questions about the definition? You can just ask by voice.
So can H just be R to the n minus 1 or below that?
That's a great question. Let's answer that. So you're really asking, so question is, let's say is R2 a subspace of R3? That's kind of what you're asking, right?
Yeah.
Okay, so anybody know how to answer that?
Yes.
Okay, so let's look at the definition. So why is or isn't it a subspace?
Well, R2 contains the zero vector, and if you add any vectors within R2, you're going to get vector within R2.
Yeah.
And then same thing for scalar multiplication.
Okay, that's true, but there's one very important thing. We didn't satisfy that. Is R1, forget subspace, is R2 even a subset of R3? So remember, R2 contains vectors that look like this, right? And R3 contains vectors, or maybe I shouldn't write equals. So R2 contains vectors that look like this. R3 contains vectors that look like this. Are the vectors in R2 actually literally contained in R3?
No.
No. So actually, no. Because R2 is not even a subset of R3. Okay, so it's a great question. And it highlights one important feature of the definition is to be a subspace. First of all, you have to be a subset. And Rn minus 1 is not a subset of Rn. They're just completely different sets of objects. So no, it's R2 is not a subspace of R3. Let's see some examples of things that are subspaces and maybe are not subspaces. Any more questions before we move on to that?
Someone's asking, what's the difference between a subspace and a subset?
A subset is literally something for the Venn diagram looks like this. So subset, okay, so X is a subset of Y if everything in X is also contained in Y. So definition, X is a subset of Y if every element of X is an element of Y. So R2 is not a subset of R3 because actually no element of R2 is contained in R3. Right? An array with 2 numbers is never contained in the set of arrays with 3 numbers. Does that answer the question?
Yeah, thank you.
So then for a subset, like for example, for a subset in R3, does that mean that just one of the variables is held to 0? Or is that nothing to do with it?
Okay, maybe you
Like
can
in order to
ask
have
that
a
again.
plane- In order to have a plane, right?
Yeah, in order. So we'll look at a few examples, and that'll clarify this. Okay, so let's yeah.
Sorry, I'm having trouble envisioning like H. Like, is it supposed to be abstract? Or are we supposed to be able to write a set of vectors H in which those 3 like things are true?
That's a great question. So as we'll see in a moment, almost all subspaces that show up are infinite. So you can't actually write it down. But we'll talk about
Yeah.
how to describe it later in the lecture, which is what a basis is.
Okay, yeah.
Yeah, that's a great question. But let's look at some examples right now. Let's look at some sets and check whether there are subspaces, right? Okay, so the set containing the 0 vector, this is a subset of Rn, right? For every n, this is the 0 vector in Rn. Is this a subspace? Well, let's check the properties, right? 0 is contained in the set, yes. If any 2 elements are in this set, then is the sum in the set in this case? Yeah, 0 plus 0 is still contained in this H, right? And if you take any element in that set, namely 0, and then multiply by a scalar, do you get an element in the set? Yes. So this is a subspace. Okay, let's, what about H equals R2, subset of R2? Is this a subspace? Well, again, when you encounter a new concept, when in doubt, look at the definition. Is R2 a subset of R2? Yes. Is 0 contained in R2? So 0 means, again, just to clarify, this 0 is the 0 vector of Rn, right? So the 0 vector of R2 is contained in R2, yes. If you have 2 vectors in R2 and you add them, do you get another vector in R2? Yes. And if you scalar multiply a vector in R2, do you get a vector in R2? Yes. So this is also a subspace. Right? So Rn is a subspace of itself. That's perfectly valid. It's a subset of itself that's closed under taking linear transformations. Now let's look at a more interesting one. Let's look at the span of this vector. So this is a subset of R2. And let's plot it. This is R2. And this subset H actually just looks like this. Right? It's all the vectors that are multiples of 1, 0. So is that a subspace?
Yes.
Yes. Anybody disagree with that? Okay, it is. I mean, you can check the 3 properties. This is a subspace. Let's look at another set. Let's look at the set of all vectors that look like this. Okay, that's a subset of R2. Every element of that set is indeed a vector in R2. Is that a subspace?
No, because we don't know if it goes through the origin.
Yeah, no, because it doesn't go through the origin, right? So no, because 0 is not in H, right? So this actually looks, I believe this set looks like this. And that doesn't go through the origin. Okay, maybe a more interesting set now. Let's look at the span of this is a subset of R3. Is that a subspace?
Yes.
Yeah. And what does it look like? Well, it looks like, so if this is x1, this is x2, and this is x3. If you take all possible linear combinations of these vectors, you get vectors that are 0 in the last coordinate. So it ends up looking like this whole plane down here. Yeah, it's not a very good picture, but yeah. So, okay, so subspaces are supposed to, geometrically, they're planes through the origin. Algebraically, they're sets that are closed under taking linear combinations. And in general, the span of a set of vectors is always a subspace of Rn. Okay, so let's write that. So in general, if you have a set of vectors in Rn, H equals the span of those vectors is a subspace of Rn. Okay, now why is that? So this is a slightly more abstract setting because now we don't exactly know what the vectors are, right? Well, let's prove this. So is it a subset? Yeah, span, if you have a bunch of vectors in Rn and you take linear combinations, everything you get is also in Rn. Property 1 is 0 in this set. Well, is it?
Yeah, couldn't we just take the linear combination of 0 multiplied by every vector? And
Exactly,
just
yeah. Just take 0 v1 plus 0 v2, 0 vk, and that's in H, right? Because it's in the span. What about the sum property? Well, let's check this, right? So suppose you have some vector, suppose you have two linear combinations in this set, right? So suppose V is equal to C1 V1 plus all the way up to CK VK. This is an H. And then you have some W that's some other linear combination. Let's call that, I don't know, D1 V1, DK VK in H. So you have two vectors, these are arbitrary vectors in H. I want to prove that the sum is also in H. Well, let's see what happens. If I add them, the key point is just by rearranging the sum, that's also a linear combination, right? Just by adding coefficient wise. CK, sorry. Sorry, CK plus DK, right? So that's also in the span, right? Which is H. So indeed, this is also true. And CV is also, you can sort of similarly check. So that's the proof, right? I just follow the definition. Is it a subset? Yes. Is 0 in the set? Yes. Whenever you have two vectors in the set and you add them, does it stay in the set? Yes. And the reason is the set was defined as the set of all linear combinations. So it's not surprising that that's always a subspace. It's not surprising that that set is closed under taking linear combinations because linear combinations of V1 through Vk are themselves linear combinations of V1 through Vk. So any questions about that proof?
Is that true that we don't even need to like include V to Vk in this span? Like even span V1 can like be a subspace of this Rn?
Be a subspace of Rn? Yeah. So I haven't fixed K, right? K could
Yeah.
be 1.
Okay.
So K for any K, right? K can be 1. I mean, it can't be 0. So because the set has to not be empty, but K could be any number.
Okay. Yeah, that's clear. Thank you.
Can
Okay.
K be greater than 1 though?
Yeah, K could be 100. K could be greater than N. K could
I
be
mean,
anything.
greater than N, I meant, yeah.
Yeah,
sorry.
K can be greater than. Why not? We haven't made any comment about whether or not H is equal to Rn yet, right? K could be anything. For any K. Does that answer the question? Okay. So now, so that's one way to get subspaces. Span of a set of vectors is always a subspace of Rn. Now there are a couple of other ways to get subspaces that are very important in the course. And I'm now going to describe them. So there are 2 important subspaces associated with every m by n matrix A. Okay, so now I'm going to describe a way that given any matrix, you can come up with 2 interesting subspaces which carry a lot of meaning. So let me say what those are. So the first one is called the column space. And this is denoted call of A is the following set. Call of A is the set of vectors B in Rm such that Ax equals B is consistent. Okay, so consistent means it has at least one solution, right? So by the way, so this is a subset of what?
Rm.
Rm, because everything in the set is an element of Rm. Okay. Now, we know many equivalent ways of thinking about this, right? So if A has columns, let's call them A1 through AN, then this is just the span of the columns of A. Right? I mean, Ax equals B is consistent exactly when B is in the span of the columns of A. So this is the same thing. So that's why it's a subspace. We just proved that any span of any set of vectors is a subspace. So this is a subspace. Any questions about that connection? Okay, in terms of linear transformations, this also has a meaning. So now suppose the matrix A has a corresponding linear transformation, TA, going from Rn to Rm in the way that we've seen many times by now. So these are the 2 associated objects, set of vectors and linear transformation. This is just the range of that linear transformation. Okay, so I'm just describing the same thing in 3 different ways, right? This is in the language of vectors. This is in the language of linear transformations. And the first one was in the language of a linear system. So that's the column space of A. I personally think of it usually as the span of the columns. Hence the name column space. So that's one important subspace.
Professor?
Mhm.
In this case, can M be bigger than N?
Yeah.
Oh.
No restriction on M and N.
Oh.
Right? I mean, just as there's no restriction on K here, there's no restriction on the number of columns.
This might be a little bit of a stupid question, but where did you get the A equals A1 to AN? I thought that we already defined that for transformations to be T of E1 and to T of En.
Oh yeah, they're the same. I just named A1 to be the first column.
Oh, okay. Okay, thank you.
So you're right. Indeed, A1 is equal to T of E1. A2 is, I mean, we might as well write it here. AI is equal to TA of EI. Yeah, you're right. So in linear algebra, this is one of the occasionally confusing but ultimately liberating things, which is every statement that we say, there will be like 10 different ways to see why it's true. And so if you find a different way, you're probably, I mean, just check, but you're probably, you may be right.
So, Professor, anything that's on any transformation that's onto is a column space of A.
No. So remember, a transformation is a function. A column space is a subspace. So that sentence doesn't actually make sense. Can you rephrase?
Oh, I was just thinking because it belongs to range of T transformation of A. Oh, A. That would mean that A is onto.
I mean, right. So we'll get to how to talk about onto in this context in a moment. But as stated, remember the range of TA is a subspace. It's not a transformation itself.
Thank you.
Okay, let me give the second thing that's called the null space. So the null space of A, denoted null of A, it's a set of X in Rn. So it's living in a different space here, such that AX equals 0. Okay, so it's a solution set of the homogeneous equation. Right, so this is and it's not immediately obvious that this is a subspace. It's a solution set. We've been thinking of it as a plane through the origin, but to really know that it's a subspace, we have to check the three properties, right? So let's check them here. Is 0 in the set? Yeah, A times 0 is equal to 0. If V and W are in the set, then is V plus W in the set? Yeah, because A times V plus W is A times V plus A times W, which is 0 plus 0, which is 0. So indeed, that's also true. And if you have a scalar and a vector V, then A times CV, well, that's just C A times V, that's C A times 0, C times 0. Which is 0. So this also checks out. So indeed, this is a subspace. Right? When in doubt, just check the definition. The solution set of a homogeneous linear system is also a subspace. So let me now, as some people are, let me now some people mentioned one-to-one and onto. Let me draw a picture of what these subspaces look like in the context of linear transformations. So here's a cartoon, or maybe I won't write cartoon since there's not that much space. So let's say I have Rn, Rm, and I have my linear transformation TA going from Rn to Rm. Okay. Now, where do these live? So the column space lives in Rm. So it lives in the codomain. So I'm going to draw it as a parallelogram just to remind you that it's a plane through the origin. And the way to think about it is, well, it's the range, right? So we drew these cartoons about the range before. Now we're seeing that actually this range is all getting mapped to a special kind of object, which is a subspace. Okay, we're just refining our cartoon that we had earlier, right? So this is equal to the range of TA. And now what about the null space? Well, the null space actually looks completely different. So first of all, the null space lives over here in the domain. And if I were to draw a cartoon of it, I would say that this is the set of, there's a very special point in the codomain called 0. And the null space is the set of all points that get mapped to 0. Okay, so this is the cartoon associated with these objects. One is a subspace of Rn, the domain. The other is a subspace of the codomain. One is the set of, is just the range of TA. The other is the set of things that get mapped to 0. So that's a cartoon. So any questions about that?
Wait, does null A have to be a plane?
Yeah, we just proved it, right? We just checked this thing in the corner. We checked it's a subspace. And I mean, a subspace is what a plane is in high dimensions. That is the definition. So indeed, yes. Null A is a plane through the origin. Any other question?
Wait, now I'm confused about what a plane is in a higher dimension.
A plane in a higher dimension is a subspace. So that is the definition. So human beings, the best definition we've been able to come up with of what is a plane in 100 dimensions is it's a linear subspace.
So it's not a R2 plane.
No, it's not an R2 plane. It's so plane, again, anything in quotes is for geometric intuition. Really, a plane and linear subspace should become analogous concepts. Okay, yeah, there's some discussion about other things that are not a subspace, like, yeah, indeed, if you take the first quadrant in R2, that's not a subspace, right? Because as somebody mentioned in the chat, you can scale by a negative number and you won't stay in the quadrant. Good point.
So is column A a subspace of Rm and null A is a subspace of Rn?
Exactly. So let me emphasize it here. This is a subspace. Oh yeah, is a subspace of Rn. And these are both subspaces. Yeah. So they're subspaces of different, I guess, sets of vectors. Yeah. Okay, so let me make this more concrete now by doing some examples. And we now want to, so I've defined these rather abstract concepts. And somebody asked a very good question earlier, which is how do you compute, how do you even write down a subspace? How do you represent a subspace? Well, one answer is you could try to write it as a span of a set of vectors. Right? That's a way to write down unambiguously a subspace. But some ways are better than others, right? As we noted, so maybe I'll ask, how do you represent a subspace efficiently? And so I'm now going to describe a way to write a subspace as a span of vectors in sort of the most efficient way possible. And this leads us to the concept of basis of a subspace. Okay, so this definition is not very complicated. It's similar to things we've seen earlier. So here's the definition. So an ordered list. So now the order of the vectors is going to matter really for the first time. B1 through Bk in H for a subspace H of Rn is a basis of H if two things happen. The first one is that the span of the vectors is equal to H. So that means that, I mean, that's unambiguously specifying H. That's something we've already seen, right? That spans of vectors are always subspaces, and a basis is a way of writing that subspace as a span of a set of vectors. But the second property is related to its efficiency, is that these vectors must be linearly independent. Okay. So the way to think about this is the first condition says that there are enough vectors to span H. But the second condition says that there aren't too many vectors. So no redundancy. Right? If they're linearly dependent, then one of the vectors would be in the span of the other ones. And then I could delete that vector without changing the span. So that would be redundant. So asking the vectors to be linearly independent is saying that they're not redundant. So that's called a basis of a subspace. So let's stare at that for a moment. Any questions about the statement?
So since it's ordered, does that mean changing the order will make it not be a basis?
No, it'll make it a different basis.
Oh, okay.
I'm just saying the order matters. Any other question?
So the basis is just a way to represent the subspace, right?
Yeah, it's a particular way to represent a subspace in an efficient way, this linear independent. Later on, we'll see that it has many other nice important properties, but for now, that's what it is. I mean, this is the definition.
Okay.
Can you clarify again what you mean by the two terms that are in quotes? Like, why are you putting them there?
Oh, okay. Let me do some examples and then it'll be clearer.
Okay, cool.
So for example, this set of vectors, this ordered list, I guess. So, okay, maybe I shouldn't put set. Is a basis of R2, which is a subspace of itself. Right? R2 is subspace of itself. Why? Well, the span of these vectors is R2, and they're linearly independent. Here's another basis. So this set, the second set looks a little different, right? If you were to plot them, the vectors look like this. But indeed, their span is equal to R2, and they're linearly independent. I mean, to check linear independence, you just see that they're already in row echelon form and there's a pivot in every column. Okay, what about this set? So is this a basis of R3?
No.
No, why not?
You don't have enough vectors.
You don't have enough vectors to do what?
To span R3.
To span, exactly. So this is not a basis of R3 because it doesn't span, right? Okay, what about the same set of vectors? Is this a basis of this subspace? Is this set of vectors, these two vectors, is that a basis of that subspace, of the span of the two vectors? When in doubt,
Yes.
check the conditions. Yes, somebody said yes. Why?
Because it belongs. H is the span of those two vectors.
Yeah, but there's another condition. They're linearly independent. So are these vectors linearly independent?
Yeah.
Yeah, pivot in every column. So is a basis of. What about this? Is this a basis of the same H?
No.
Why not?
The last two make it so that it's not linearly independent.
Exactly. Is not a basis of this because it's not linearly independent. Okay, so that's what I mean by not too many or no redundancy, right? This set of vectors is redundant. Indeed, the span of these vectors is equal to H, but it's not a minimal set of vectors that span H because you can delete the last vector and you still get the same span. Does that answer the question that was asked previously?
Yeah, it makes sense. Thank you.
Okay. So these are some examples of bases. So to be a basis, it's like the Goldilocks theorem, except restricted to H. So now you don't need the span to be all of Rn, you just need the span to be H, and you still need them to be linearly independent. So that's a basis. And here, okay, if I give you a subspace, does it have a unique basis?
No, because you can change the order.
Correct? So the answer is no, you can change the order. But there's actually some more stuff you can do. What else can you do? I mean, change the order of the vectors. But
you can also scale one of the
you can also scale them. Can scale. So you actually have infinitely many bases of a given subspace. And actually, you can even just, I mean, these two are two different bases of R2, right? So it's not just scaling. You can actually take, as long as you take, I mean, we'll discuss this in a little after the course. You can actually, if you take linear combinations, in a way that you can, I mean, you can generate infinitely many different bases. We'll discuss it more later. Scale. Okay, so actually every subspace, well, okay, every subspace that has a basis actually has infinitely many of them. So basis is not a unique thing. So we will prove the following things after the midterm. These are important. Every subspace has a basis. And maybe it may have many actually. Actually, I'm sorry, there's one exception to this. There's one subspace that doesn't have a basis. Can somebody tell me what that is?
Is it just the zero vector?
Yeah, every subspace that's not zero. Okay. Just the zero vector that can't have a basis because the zero vector is linearly dependent. And more importantly, every basis of a given subspace has the same number of vectors. Okay, so we'll prove this in chapter 4, I guess. But this is a very important fact that even though there are lots of different bases, they all have the same number of vectors. We'll prove that later. It's not completely obvious. So, for example, it's not a coincidence here that the two different bases of R2 both had two vectors. Okay, so this second fact allows us to assign a number to every subspace, which is the size of a basis for that subspace. And this is called the dimension. Okay, so we've been throwing around this idea of this is a one-dimensional, this is a two-dimensional object, et cetera, et cetera. The rigorous definition of dimension is the size of a basis. Is the number of elements in any basis of H. They all have the same number of elements. Okay, so let's now revisit these in terms of dimension. What would the dimensions be? Well, so let's write down the dimensions. Well, here this would be 2 because they have a basis with 2 elements. This is not a basis, so it doesn't count. This H here has a basis with 2 elements, so it has 2-dimensional. And this is not a basis, but you know okay, I guess all the dimensions turned out to be 2 in this case. But in general, for example, the dimension of Rn is equal to n because the standard basis is a basis. So this lines up with our intuitive notion of dimension, that Rn is n-dimensional. So any questions about the definition of dimension of a subspace? Okay, so what have we achieved? We've defined a subspace, we've defined a basis, and we've defined 2 interesting subspaces, the column space and null space of a matrix. So the final thing I want to present is how do you actually find a basis of the column space and find a basis of the null space of a given matrix. Let's begin with the null space. It's actually easier. So let's look at a 2x4 matrix. So there's a 2x4 matrix. And remember, the null space is the set of solutions. In this case, where will they live?
It'll live in Rn.
Right, but in this case, what is n?
Oh. 4.
4. Set of vectors in R4 so that AX equals 0. So that's just a solution set, right? So I know how to find a solution set. You do row reduction. So there are some pivots. Okay, it's not an RREF. You do one more row operation. You subtract, I guess, 3 times the second row from the first row, and you get 7 here. And you get 1 minus 1. Let's call this matrix R. This is an RREF. And so, well, I know how to find the solution set, right? There are some pivot variables and some free variables. And so if I now, we did this in week 1, the variables are, I guess, x1, x2, x3, and x4. You can express the pivot variables in terms of free variables. You get x1 equals, I guess, minus 2x2, minus 7x4, and x3 equals x4, and the rest are free. Okay, so now let's write the solution set. So what is this? This is a set of vectors. What do they look like? Well, the first coordinate is x1, which is minus 2x2 minus 7x4. Second coordinate is x2. Third coordinate is x4. And last coordinate is x4, where x2 and x4 are any real numbers. Okay. So now I want to, I want this to be a span of a basis of it, right? Can I write this as a span? Anybody see how to do that? So this is my usual way of writing a solution set parameterized by free variables. Can I write it as a span?
Is it the span of the pivot columns?
Well, no, right? That wouldn't make sense because the pivot columns are vectors in R2, and this is something in R4.
I think maybe you can write it as the linear combination of x2 and x4, and like it will be a span.
Yeah, so the idea is that these x2, x4 are free variables, right? So I can just rewrite this by pulling the x2 and x4 out. This is the set of x2 times the vector. So now I'm going to collect the coefficients of x2. So minus 2, 1, 0, 0, plus x4 times minus 7, 0, 1, 1, so that x2, x4 are real. So it's a sneaky trick. It's actually just arithmetic, but now it's obvious that it's a span, right? Nice. So let's give these vectors a name. Let's call them v1 and v3 since they correspond to the first and third. The second and fourth. So v2 and v4. We could have called them something else, but let's call them that. So that looks nice. I expressed the null space as a span of 2 vectors. I just squinted my eyes and already I knew how to do it, it turned out. But there is a lingering question, which is why are they linearly independent? To be a basis, you need to be 2 things. You need to span the space and you need to be linearly independent. Why are they linearly independent?
Because we have more solutions in the trivial solution?
No, I'm saying that you don't have that, right? I'm saying they're linearly independent, so you don't have more solutions in the trivial solution. Why don't you?
Well, in this case, there's only two vectors, so they're not multiples of each other.
That's true. In this case, there are two vectors that are not multiples of each other. That's the correct answer. Can you see a more general pattern for why, and what's the general reason why if you do this, you always get linearly independent vectors?
Because
Oops, sorry.
Because n, thank you. Because n will be less than m, I think.
That doesn't imply that they're linearly independent, right? I mean, the too many vectors theorem says if n is bigger than m, then they're not linearly independent. But if n is less than m, it doesn't say anything.
Is it that, like, because you've defined x2 and x4 to be free, that you'll eventually have like a 0 in one column, but then a 1 in the other column, and then you can't get to 0 without setting both equal to 0?
It's even simpler than that, but you're on the right track. The answer is, what does a linear combination of these two vectors look like? Well, we already wrote it, right? So x2 v2 plus x4 v4. Well, it looks like this vector, right? And linear independent means this is 0 implies that the coefficients have to be 0. But it's like actually staring at us. Two of the entries here are the coefficients themselves. So this implies x2 equals x4 equals 0. That's it. Okay, so this is you kind of get it for free. That when you, in this approach, the free variables will always appear as entries of the linear combination. And so if the linear combination is 0, all the entries have to be 0. So then the coefficients have to be 0. So then these are linearly independent. And you can see that this will always work because the free variables, which are the coefficients in the linear combination, always appear as entries of the linear combination. So what's the summary or general method? To find a basis for the column space of A, there are two steps. One is find the general solution of the homogeneous system. And then the second step is rewrite it as a span of vectors with the coefficients corresponding to free variables.
Professor,
Mm-hmm.
should this be finding a basis for null A?
Oh, sorry, null A. Whoops. Yeah,
Okay.
null. Sorry. Thank you.
Thank you.
Okay. And now by the argument in the previous slide, so you already got the spanning, and these are automatically linearly independent because the coefficients in the linear combination appear as entries of, of the vector. It's of the linear combination. Of the resulting vector. So it's this argument written over here. So that's it. It's actually, row reduction just does it for you. It's a week 1 level thing, and you get that they're linearly independent for free. And what's an important consequence? Consequence is that the dimension of the null space of A is equal to the number of free variables. That's an important consequence. Any questions about that?
So what about like when there's no free variables?
When there's no free variables, the dimension of the null space is 0, which is possible, right? Because the null space can just be the zero, the one, the zero subspace. It's possible, right? So I should point out the dimension of the zero subspace is 0. So no free variables means the dimension is 0. That's perfectly valid.
Okay.
Okay. And I guess I'm running out of time, but let me quickly mention how to compute the column space. So this is conceptually more complicated, but computationally easier. Let's look at an example, A. Let's look at this matrix. And let's say its columns are A1, A2, A3, and A4. And let's say I want to compute the column space. Okay, so it's not, so first of all, the column space is the span of the columns, right? So why can't I just output the columns as a basis for this for the column space?
There might be some linearly dependent or like unnecessary vectors.
Exactly. They might be linearly dependent. So the only issue is they might not be linearly independent. Okay, so I'm gonna just do row reduction to compute the reduced row echelon form. Not clear how that would be helpful. Here I just subtract the third row from the second row from the third one, and then I guess I want to do RREF, so I'll subtract 3 times again. So I get 1, 2, 0, 7, 1, minus 1, 0, 0. That's the reduced row echelon form. And this has some different columns. Okay, so the first question I want to ask is the column space of A equal to the column space of R? Okay, some people said yes. We know that the column, I mean, okay, we should, I mean, maybe people are saying yes. And the reason you might be saying yes is that the null space of A is equal to the null space of R, right? Because they're both solution sets, and the solution set doesn't change when you do row operations. But actually, the answer to this is no, they're not the same. Row operations don't preserve the span of the columns. And you shouldn't be surprised by this because everything in the column space of R has a 0 in the last entry, whereas that's obviously not true of the column space of A. In fact, A4 is not in the column space of R. Row reduction does not preserve the column space. It preserves solutions of linear systems, which explains why it preserves the null space, but it doesn't preserve the column space. So is this totally useless? Well, it turns out no. And this is a pretty sneaky kind of reasoning. Let's compute a basis for the, so let's draw a line here between these two different worlds. Let's compute a basis for span of for the column space of R. Okay, so here it's an REF. These are pivots. And now, okay, so I have that span of R1 and R3 is equal to column space of R. Why is that?
Because those are the only pivot columns in R.
Those are the only pivot columns. That's one way to think about it. But it's actually more to do with the rows. So the reason is because there is a pivot in every non-zero row of R. And these are the pivot columns. So concretely, what do I mean by what do I want to emphasize? I want to emphasize that these linear systems, so 1, 0, 1, so, and if you put R2 and 1, 0, 1, sorry, there should be zeros here. And here, if you put R4, these are consistent. And the reason is that you can ignore the 0 rows. Okay, that's not going to change consistency. And in every non-zero row, when you restrict attention, yeah, so I guess I guess I mean, if you restrict attention to R1 and R3, there's a pivot in every non-zero row, so you'll always be consistent. Okay, so that's fact number 1. Okay, fact number 2 is that these are linearly independent. And the reason is that, well, for example, if you look at the matrix with these as columns, there's a pivot in every column. So remember, linear independence is the same as having a pivot in every column. Okay, so indeed R1 and R3 are a basis of the column space of R. So this is a general fact. If you look at the pivot columns, they give you a basis for the column space in the reduced row echelon form. Okay, but this is some sort of a, why is this relevant? I mean, we're interested in the column space of A. Right? So now I'm going to do something very sneaky. I'm going to use the fact that the null space of A is equal to the null space of R. Now, what does that mean? So this fact is going to allow me to translate statements from one side to the other. So I know that R2 is equal to, let's say, C1 R1 plus C3 R3. Right? And I can write that, the trick is I can write that as a linear dependence. I can write that as an element of the null space of R. I can write that as saying that the matrix R times the vector C1 minus 1 C2 0 is equal to 0. And now this is the really sneaky part. I can now cross this line by using the null space fact, because this means that the same vector is in the null space of A. But now this tells me something about the columns of A, right? If I write down what this says, it says that A2 is the same linear combination of the corresponding columns of A. Okay. So that means this is a very actually quite a subtle thing. I use this fact to translate a linear, to move linear combinations from the R world to the A world. And I can do the same thing with A1. Sorry, I guess in this case 4. And so I can actually recover this fact. Span of A1, A3 equals column space of A. And by similar reasoning, I'm sorry I've run out of time. I'll go over more detail next time. I can also transfer the linear independence, A1, A3, or Li. And together, this means that the pivot columns form a basis of A. So the summary is very straightforward. Even though the column space of A and the column space of R are different, the pivot columns give you a basis for the column space. So general method, pivot columns. So columns of A corresponding to pivot columns of R. Corresponding to pivot variables are a basis of the column space of A. Okay, very sorry to go so much over time. That's really awful. I'll end early next time, but yeah, that's it.